Suppose we toss a coin one time. Now, how many outcomes are in the sample space? So we toss a coin one time, so let's think about what the sample space is. So if you toss a coin, you either get heads or you get tails. So there are 2 outcomes in the sample space. Easy enough. Now let's take a look at the next one. Suppose we toss a coin 3 times. How many outcomes are in that sample space? Well, we're going to find that they're going to be 8. So why 8? So here's where we're going to start building a tree diagram. So because you're tossing a coin 3 times, this can be thought about as being a 3-stage experiment. The first stage is what you can get on the first toss. The second stage is what you would get on the second toss. And the third stage is what you would get on the third toss. Now I'm going to build my tree diagram going across the page or horizontally. You can also build these diagrams going vertically or down the page. So I like to put a dot where I'm going to start. Alright, so let's think about that first stage, which would be that first toss. What could happen on the first toss of that coin? Well, you could either get a heads or a tails. Because there are 2 outcomes, I'm going to draw 2 branches from that initial dot, and at the end of the branches, I'm going to put what the outcome is. Heads or tails. Now notice that I am keeping the outcomes kind of stacked and aligned, so we want this to kind of look orderly and neat so that way we can get an idea of like kind of what's going on in each stage of the experiment. So that's what can happen on the first toss of the coin. I could get a heads or a tails. Now what could happen on the second toss of the coin? Well, you toss a coin the second time, you could get a heads or a tails, right? You still have those 2 outcomes. So from both of these first outcomes, I'm going to draw 2 branches to indicate what could happen on the second stage if this is what happened on the first stage. And then at the end of the branches, I'm going to put what the outcomes are. So on the second toss, I could get heads or tails, and that's if heads had happened first. Down here, I could get a second toss of heads or tails, and that's assuming tails happened first. Now at this point in time, if my experiment were over, I would have 4 outcomes. So this would be if I was only to toss the coin twice. The outcomes that were possible would be heads and then heads again, heads and then tails, tails then heads, and then tails and tails. On this particular example though, I'm going to be tossing the coin 3 times. So I want to extend these branches one more time. So on the third toss of the coin, I could still get heads or tails. So I'm going to branch 2 branches from each of these that I had built previously. Okay, so here's where we start trying to squish it in. The more you do these, the better idea you'll have about spacing. So again, I'm still drawing my branches about all the same length over, so that way for all of the different outcomes on that stage, I have them all stacked. So these are going to be my 8 outcomes. I'll list them over here. I could have heads, 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 tails, heads, tails, heads. Now, where am I getting these? I'm starting here at the beginning node, and I'm just walking along the branches until I get to this final node. So this next one down here would be heads, tails, tails. Now coming down here to this lower part, there would be tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So there's my 1, 2, 3, 4, 5, 6, 7, 8 outcomes. Now I want you to notice when I listed the outcomes, I didn't put commas in between the elements. We kind of squish it all together because the experiment, you have to toss the coin 3 times before your experiment is over. So all of those together is 1 outcome. So like for instance, if I were to start listing them over here, I would have, okay, I could have heads, 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 and then I'm going to put my comma, and then I'm going to list the next one. So I could have heads, heads, tails, and then I'm going to list my comma. Okay, so notice at this point in time, because it's 3 stages, I basically have 3 symbols in each outcome to indicate what's happening on a particular stage. Okay, So I'll just write etc. here. The actual outcomes we can just pull over there. Now for this next one, suppose we toss a coin 10 times, how many outcomes are going to be in that sample space? Now at that point in time, because you're tossing a coin 10 times, now this is only tossing a coin 3 times, so imagine extending this tree out 7 more times. Each time you extend it, you have to draw 2 branches, and then 2 more branches, and then 2 more branches. That's going to be a lot of branches by the time this is over. So if I was to toss a coin 10 times, and I want to know how many outcomes there are, we would not want to make a tree for this. That's going to be way too many branches. I still, though, want to answer the question of how many outcomes are in the sample space, but on this one I'm not going to be able to necessarily draw a tree to visualize it. But the tree kind of helps us internalize what's going on in this counting principle that is going to help us answer this question about how many outcomes are in that sample space. The counting principle, which is also sometimes I've seen in other textbooks called the fundamental counting principle, because it's so important in order to help us to kind of see what's going on when we run experiments. And I'll start abbreviating it FCP for fundamental counting principle. What it says is if the first experiment can be performed in M distinct ways, and the second experiment can be performed in N distinct ways, then the 2 experiments in that specific order can be performed in M times N distinct ways. So in other words, when an experiment is done in stages, the total number of outcomes in the experiment can be found by multiplying the number of possible outcomes on each stage. So how does that relate to this coin scenario? Well, in this one right here, if I'm going to be tossing the coin 3 times, maybe I'll use blue here. So since I'm doing this 3 times, this is going to be a 3-stage experiment. So I'm going to put down 3 blanks indicating each of the possible stages. On the first stage, there are 2 possibilities for the coin, heads or tails. On the second stage, there are 2 possibilities for the coin, heads or tails. And on the third stage, there are 2 possibilities for the coin, heads or tails. If I multiply these numbers together, I will get how many outcomes there are overall when running this experiment. 2 times 2 is 4, 4 times 2 is 8. There are 8 outcomes total, and then that's what was actually verified for us in the tree that we built. So let's take a look at this next one. If you toss a coin 10 times. So if this is 10 times, this is going to be a 10-stage experiment. So we could, in theory, put down 10 blanks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On each of those stages, you're going to be tossing a coin. So there are 2 outcomes on the first stage, 2 on the second, 2 on the third, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. If you multiply those all together, that will tell you how many outcomes you have total. So this actually, the shortcut for this would be 2 to the 10th power, right? Because I've got 10 2's I'm multiplying together, and 2 to the 10th power is 1024. That's a lot of outcomes. So we don't necessarily want to draw a tree for that situation, but trees can help us kind of see how the fundamental counting principle is working, and why we multiply in order to get the overall counts.